Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, we're back again to conduct lecture 4 in week 2 of this course. This particular lecture, we're going to focus on a review of the elasticity of materials. So if you're a materials scientist or a mechanical engineer, you probably already know a lot of the material that we're going to discuss. But if you're a chemist or possibly a biologist and you're interested in using AFM for your experimental work, maybe this is a good chance to review some important ideas and concepts that are really fundamental to our understanding of how a tip interacts with a substrate. The fundamental dilemma that we have to deal with, that we have to sort out here, is the fact that when a tip is into contact with a substrate, the size of that contact region is on the order of nanometers. And so the issue is how you deal with that in an appropriate way. And you basically have two choices. One choice, you can pretend that the tip is made up of the atoms and the substrate is made up of individual atoms, and perhaps not all the tip atoms are identical, and perhaps not all the substrate atoms are identical. And you then have to calculate the interaction forces between the tip atoms and the substrate atoms using a lot of the formalism that we discussed in the first week of this course. The trouble is, of course, you don't know the chemical composition of the tip or the substrate at an atom-by-atom basis, so this approach is rather difficult to achieve. On the other hand, you can treat the tip and the substrate relying on bulk approximations. Here you treat the substrate as a flat slab of material. You'll treat the tip as a spherical object of radius r sub tip. You'll apply a force to the tip and you'll ask, what are the interaction forces between this perfectly round tip and this perfectly flat substrate? So the problem with this bulk approach is, of course, that you're going to neglect the atomic corrugations that exist on the tip. You're going to neglect the atomic steps and the atomic scale features that may be on the substrate. And you're going to sacrifice that in order to achieve a numerical model that better describes the tip-substrate interaction. So atomic force microscopy sort of jumps back and forth between these two different views. And for the remainder of this lecture, we're going to focus on the bulk continuum approach to this problem. And we're going to review some of the basic ideas that underlie this contact mechanics that's been developed since the late 1880s. So this material is reasonably well understood. It's in virtually all introductory textbooks in materials science. We're just going to sort of summarize some of the important results that are particularly relevant to the atomic force microscope. So to begin with this review, let me remind you that there are basically 3 types of external forces that deform solids. One force is a force that's applied normal to a cube of material. We assume that the cube has a cross-sectional area A. We apply a normal force, as indicated in the first panel in this slide. There are 2 other deformations and forces that can be applied. One is a tangential stress, and the other is sort of a hydrostatic pressure that's applied equally to all faces of the cube. Those 2 deformations are not terribly interesting for atomic force microscopy, and what we do is we'll focus on the normal stress applied perpendicular to the plane of a cube. The dimensions of the cube are L by L by L, and the question is simply, what is the elongation of the cube in the direction of the applied force? That elongation or that deformation is referred to as dl, and we can calculate the ratio basically of the stress to the strain. So the stress is defined as the normal force divided by the cross-sectional area. The strain is defined as the change in length divided by the original length L. And the ratio of those two quantities is just equal to something called the Young's modulus of the material. So the Young's modulus, or the elastic modulus, as it's often referred to, is a number, and it basically describes the resulting strain that's produced when a particular stress is applied. So the units of Young's modulus are force per unit area, and the forces are measured in newtons, areas are measured in square meters. So the units of Young's modulus would be newtons per meter squared, which is equivalent to a Pascal. So 1 Pascal is equal to 1 Newton applied over a cross-sectional area of one square meter. So this defines the Young's modulus, and the value of Young's modulus for any given system is then going to determine the deformations that system will undergo when a force is applied. It's important to have some rough understanding of orders of magnitudes of the Young's modulus, and there are very nice charts on the internet that provide you with this sort of survey information about the size of Young's modulus. So this particular view graph just shows you Young's modulus for the elements. You can just, by visually looking at the slide, everything's color-coded so it's easy to comprehend. You can just, by looking at this slide, recognize that the Young's modulus of many elements that exist in their solid form, the Young's modulus is on the order of 50 to 100 gigapascals. There are some elements in the transition metals that are clearly much harder. They have a much higher Young's modulus. They approach 400 to 500 gigapascals. It's also important to know Young's modulus by material class. And in this particular slide that I also found on the internet, on the y-axis we're plotting Young's modulus. Young's modulus varies from 0.01 gigapascals. 0.01 gigapascals is about 10 megapascal. That's a very soft material. The upper end of this chart is 1,000 gigapascals. 1,000 gigapascals is a very hard material. It's approaching it's approaching diamond. And what you can see from this is, depending on whether you're dealing with rubbers or polymers, ceramics, metals and alloys, you have different Young's modulus that's appropriate. And it's kind of useful to know that the span of Young's modulus that's required to describe these different classes of materials, that Young's modulus varies over about 5 orders of magnitude to adequately describe how these materials would respond once they're deformed. Another table that I find useful is the Young's modulus for various materials. These tend to be engineering materials or materials that are appropriate for AFM purposes. And this is from a chart that actually that I had hanging up in my lab for many years, because as we work through the design and construction and various AFMs, we often needed to know the modulus of some of these parameters that you typically use in AFM experiments. So I just provide that list here. It might be useful for some of you to know about these numbers. They're sometimes a little bit more difficult to find than the modulus of let's say, the elements. Another very important quantity to understand in this discussion of elasticity is you have to realize that a stress applied to a solid produces strains, produces deformations in lateral directions. And I tried to indicate that idea with this diagram, in which I apply a normal force to a cube. The dimensions of the cube are W by D by L in this diagram. And basically what happens once this normal force is applied, the dimensions of the cube change. right? So we've already talked about the elongation of the cube. So the length of the cube goes from L to L plus DL. But in addition, the lateral dimensions, W and D, also change as indicated. And it's kind of useful to know how much those lateral dimensions change for a given change in the dimension parallel to the applied force. And the answer to that question is described by a quantity called the Poisson's ratio. Poisson's ratio is often written as the Greek letter nu, and it's just defined as the ratio of the lateral change in dimension to the change in dimension longitudinal or in parallel to the direction that the force is applied. Typical values for the Poisson's ratio, again, I go to the web and I find this very nice chart for Poisson's ratio for elements. It's color-coded, so you can just look at it and you can recognize immediately that the Poisson's ratio for a large number of the elements is on the order of 0.3 to 0.4. It's a dimensionless number, and it just describes the lateral deformation for a given deformation parallel to an applied force. By material class, Poisson's ratio by material class, there's also a very nice chart that summarizes that result. The materials that we tend to study using atomic force microscopy, those materials are sort of boxed in by that gray rectangle at the top of this chart. And what you can see is that the Young's modulus for most materials that we deal with in AFM, they typically range from maybe 0.1 to 0.45 values for Poisson's ratio. Typical value for Poisson's ratio is on the order of 0.3. So for most solids that you might deal with, a good approximation for Poisson's ratio. If you don't have an exact value, a good number would be something on the order of 0.3. It's probably worthwhile to run through a simple example of how you use these various values to do a simple calculation. So in this case, I consider a 25 millimeter cube. It's made up of some material. Don't know what the material is. What we do is we rig up an experiment where we apply 100 newtons of force to the cross-section, perpendicular to the cross-sectional areas of this cube. And in the process of applying that 100 Newton force, we measure that the cube extends by about 200 nanometers. So we've got a delta L in this case of 200 nanometers. And with that information, then you can ask a variety of questions, and then it's pretty simple to work out the answers. You can ask, what is the normal stress applied to the cube? The normal stress is just the force applied divided by the cross-sectional area. So we calculate that the stress in this case is about 1.6 times 10 to the 5th Pascal. We can ask, what is the resulting strain of the cube? Well, we know the change in the length, and we know the initial length, so the strain is just delta L over L. It's about 8 times 10 to the minus 6. It's a dimensionless number. From those two quantities, the stress and the strain, you can then estimate Young's modulus for this material. And for this particular example, the Young's modulus comes out to be about 20 gigapascal. And then lastly, you can ask, what is the lateral, the change in the lateral dimensions of the material? So we're basically asking, how does the width or the height of the block change when 100 newtons is applied along the length of the block? That requires us to know Poisson's ratio. And in this particular case, we're assuming Poisson's ratio is about 0.3. So we would estimate then that the change in the height and the width of the block is about 60 nanometers. So that's how you would use these concepts in order to sort through a really simple problem in elasticity. It's also useful to have in your mind a microscopic model of what Young's modulus is trying to capture. And I try to suggest such a simple model in this particular slide. In particular, I'm going to view the solid as comprised of a bunch of atoms that are interconnected one by another with springs. The spring constant in this particular case is going to be designated by the parameter K with the subscript atom. And what we'd like to be able to do is we'd like to be able to relate that effective spring constant to, let's say, Young's modulus that we would measure for this bulk cube of material. So the way to do that is you actually have to define how much force is applied to each atom in the solid, and that calculation is basically done in the equations here. You have to take the force that you applied, that's what you measure. You have to calculate how many atoms there are in the cross-sectional area A. That's worked out in the first set of equations. What you can then do is you can set up a relationship that defines the force per atom in terms of the change in the spacing A0 between the atoms. And that change in the spacing between the atoms is designated by the parameter dA0 in this set of equations. And if you work through the arithmetic, I think you can very quickly recognize that the ratio of the stress to the strain that shows up in this simple derivation, that can be identified with Young's modulus E, and it gives rise to a very simple result that says that the effective spring constant between atoms is equal to Young's modulus E times the interatomic equilibrium spacing A0 between the atoms. So ultimately, the parameter that you measure in the bulk, E, Young's modulus, has to be related back to these interatomic spring constants, K. This is a very simple example that neglects lateral coupling of atoms with planes of atoms above and below an individual plane, but at least it gives you a flavor of how these things are interconnected. It's also useful to try to relate these bulk properties that we measure back to microscopic properties, let's say, that describe how two atoms interact one with respect to another. So a standard interaction potential for two atoms is this so-called Lennard-Jones interaction model. It's also referred to as the 12-6 model, because it models the interaction forces as 1 over z to the 12th minus 1 over z to the 6th. So it's referred to as a 12-6 model, and often it's referred to as a 12-6 model in the literature. This model has two parameters which must be adjusted to fit some experimental data. One parameter, U0, is the depth of the interaction potential well. The other parameter is this value of sigma that appears in the top equation in this slide. So it's pretty straightforward to predict sigma in terms of the equilibrium separation between atoms. The equilibrium separation between atoms in the solid is going to occur when the atoms, when there's no net force acting on the atoms, and the resulting separation between atoms in that case is designated by this lattice constant parameter A0. So it's a pretty simple result that you can predict the parameter A0, which is a measurable quantity, in terms of the theoretical parameter that's used to model the Lennard-Jones potential, that's sigma. I actually worked through the derivation of that in this slide, where I start with the interaction potential. I take a derivative to calculate the exact forces. I set the force equal to 0, and that gives me the relationship between A0 and sigma that I want. And then, I like to predict the depth of the potential well that's appropriate. How do I select the parameter U0 in the Lennard-Jones model? Well, one way to do it is to realize that in equilibrium, right, the atoms behave as a spring system. So if you apply a force dF, there's going to be a deformation dz, and the proportionality constant between the applied force and the resulting deformation to a good approximation is just going to be the spring constant that we've just calculated. So you can work through the arithmetic on this, and at the end of the day what you find is that the depth of the well is in fact related to the Young's modulus E and the interatomic spacing A0 by the equation that's given at the bottom of the slide. Now this equation is probably a little bit simplistic, but I'm not so much interested in exact numbers. I'm just trying to get you to realize that all these macroscopic things that you can measure can in principle be related back to microscopic quantities. In this particular view graph, I just take these expressions that I derived and I just try to calculate what the parameter U0 would be, what you would predict for the parameter U0 based on, let's say, gold. So I looked up the Lennard-Jones potentials, or the parameters for a Lennard-Jones model in gold. I found those in the literature. I also looked up the elastic modulus of gold. It's about 80 gigapascals. That's a value that you find from the handbooks. And when you apply this very simple model, you find out that U0 should be on the order of 1/10 of an EV. That's probably about 45 times too small compared to values found in the literature. And I think it just indicates that this model, although qualitatively correct, is far from being accurate, right? You need to include many more effects in order to make this connection. But nonetheless, you know, these macroscopic values for Young's modulus in principle can be always be related back to microscopic parameters that describe how atoms interact one with another in a solid. So up next in this set of lectures, we're going to conduct an introduction to contact mechanics. We're going to try to describe the deformations that result when two materials come into contact, one with respect to another. We're going to need to know both the Young's modulus and the Poisson ratio for these materials in order to accurately predict the deformations that occur. So hopefully this lecture provides those of you that don't have a background in this area with the necessary material that will allow you to appreciate the next lecture.